Analysis of sorting algorithms. In the last few lectures, we learned about a lot of sorting algorithms. Specifically, 12 different sorting algorithms is what we learned. Here, we are going to put all these 12 together and we'll try to understand what are the characteristics of all these algorithms, how they are different. We'll also go through the time complexity analysis, space complexities, its stability, whether it is in place or out of place, and so on. And then we'll see under what situations, under what circumstances should you use each of those algorithms, because you need to know why each of those sorting algorithms are special. In detail, we discussed in the particular lectures. Here we'll just go through all of those, just that you get a comparative analysis of all the algorithms, right? We'll start with whatever we started with our lectures with. First one was bubble sort. So in case of bubble sort, what is it that we followed? We bubbled up the largest element to its right place after each pass. So after the first pass, the largest element gets bubbled up to the right place. After second pass, second largest element gets bubbled up to its right place, and so on. And this is where the name bubble sort came from. What did we learn about the time complexities? Let us draw it here. What did we learn about the time complexities? In case of bubble sort, we learned that in case best case, what is the best case time complexity? It is order of n. How is it order of n? Best case is order of n because in case your first pass itself shows a sorted list, you would exit from the loop. In that case, it is order of n. What about the worst case? In worst case, you may have to keep bubbling separately for each of the n passes. That means n into n will become order of n square in worst case. What about the average case? In average case, again, it is order of n square only. What is the reason? Because you have to keep doing this swap and bubbling. So each pass will be order of n. The total number of passes will be comparable to order of n in average case. Even if you consider n by 2 passes, it will be order of n. So average case is also order of n. What is the next thing? What about the space complexity? As far as space complexity is concerned, it is having order of 1 space complexity. Why is it order of 1? Because you are not consuming any additional space. Whatever is the array provided, you are going to do all the bubbling in that array only. That is why space complexity will be order of 1. Next thing is about stability. Is this stable algorithm? Yes, it is stable because why is it stable? Your elements, in case there are two elements which are of the same value, you won't be exchanging the positions of those elements. Whatever was the first among them will be the first among them in the final sorted list as well. This is why it is a stable algorithm. And the last thing is whether it is in place or out of place. Is it an in place algorithm? So we learned it is in place algorithm. Why is it in place? It is in place whenever you don't use extra space. So in case of bubble sort, you don't use any extra space. So it is in place algorithm. This is it about bubble sort. And what did we learn about it? It is a simple algorithm, but it is inefficient. So you should generally not use bubble sort. You will generally use it only if you want to implement, but you don't have time. You just want to write a very basic algorithm. Then bubble sort is an easy option. Otherwise, because of repeated swapping, it is not an efficient algorithm. So the problem is swapping. At each pass, you may have to do even order of n swaps. So that is where bubble sort becomes inefficient. What is the next thing that we considered? We considered selection sort, right? What about selection sort? In case of selection sort, we saw that the number of swaps is fewer in selection sort if you compare with bubble sort. How did it work? It selected the smallest element and placed it the right place. So after each pass, it selected whichever is the smallest element from the unsorted part and it placed it the right place in sorted part. This is how selection sort worked. So because of that, we saw that while it was selecting the smaller elements, and directly swapping with the right position, the number of swaps decreased considerably compared to bubble sort. But still, it is a slow algorithm, and the problem is that best worst average in all cases it is having order of n square as time complexity. So why is selection sort not having order of n as best case? Because even if it is in the totally sorted order, still you have to keep doing this. You have to find the smallest element, you have to swap it with the right place. Even if the order is right, you have to keep doing this process, and because of that, even in best case it is order of n square, right? What about space complexity? It is not using any extra space because whatever work gets done inside the array that is given as input. Because of that, space complexity is order of 1. Is it stable? Bubble sort was stable, but selection sort is not stable, and the reason is that you are swapping whichever is the smallest element to its right place. So this swapping is not like the bubble sort swapping, which was between adjacent elements. Here, swapping is done between some random elements, because of which even two elements with the same value may get two different positions. So the ordering may be altered, because of which it is not stable. What about in place, out of place? Is it an in place algorithm? Yes, it is in place because you are not using any other space to do the sorting. So is space complexity same as in place? No, it is not. So we'll see it in the coming algorithms. If you had seen the previous lectures, you would already be knowing, but we'll see in the coming point whenever we reach the. Next is insertion sort. So what about insertion sort? Insertion. In case of insertion sort, what did we learn? Insertion sort will work similar to the way you sort playing cards whenever you keep them in your hands. So you'll take the card whichever is available, you'll insert it into the right place. So that is where the name insertion sort comes from. We already learned in the previous lectures that insertion sort is very efficient, especially when the data set is small or when data set is almost sorted. So in both these cases, whenever it is a nearly sorted or almost sorted array, or if your data set is small, in both these cases, insertion sort is very useful. And we even saw that insertion sort is used as part of many other sorting algorithms because of this property. So insertion sort is a useful sorting algorithm. Compared to bubble sort and selection sort, insertion sort is way more useful. What is the best case? In best case, if you have already sorted list, inserting would become an order of 1 task. Hence, the total time complexity will be order of n. What about the worst case time complexity? Worst case time complexity will be order of n square. This is the negative side of insertion sort. Average case is also n square, but the point is whenever you have small data set or an almost sorted data set, that is when insertion sort is useful. What about the space complexity? You are using the same space, no additional space, so constant space. Is it stable? Yes, it is stable, because what if there are two elements which are of same value, they will maintain the positions. Why? Because you are inserting to the right positions. If you have two elements of same value, you will insert one after the other. Next thing is, what is it in place or not? Yes, it is in place because it is not using any extra space. Whatever sorting is being done is done inside the sorted array only. Next thing is merge sort. Merge sort. What about merge sort? In case of merge sort, we saw that it is a divide and conquer algorithm. Whenever you got an array, it tried to divide it into two parts, tried to merge them later. It kept dividing till it has only one element and then started the merge process. So about the efficiency of merge sort, we already know merge sort is very efficient algorithm, and the speciality of merge sort is in all cases it maintains order of n log n. So in best case also it is n log n because you want to do complete merge process. In worst case also it is n log n, which is much better than n square time complexity, right? What about average case? Here also it is n log n. What about the space complexity? So merge sort procedure, for merging, it is taking additional space. It is copying elements to extra array. So it is taking additional space, which is order of n. Why is it order of n? Because whatever be the size of array, initial array, that much extra space is required to copy all the elements. So that is why it took order of n extra space. So this is space complexity. What about stability? Coming to merge sort, it is a stable algorithm because you will maintain the order if you have two elements of same value. Is it in place? No, it is not in place because in order to do the merging, you are taking elements to a separate space. From there, you are starting the merging process. That is why it is not in place algorithm. Which is the next algorithm that we considered? It is quick sort. So in terms of quick sort, what did we learn? Again, another divide and conquer algorithm. But how is it different from merge sort? It is going to find a partition point, a pivot. Then using this pivot, it will partition the array. How will it partition? It will partition such that the pivot will be at the right position. Whichever elements are to the left of pivot will be smaller than pivot. Whichever elements are there to the right of pivot will be larger than pivot. Then you have to continue this process till your complete array is sorted. This is what we did in case of quick sort. Then what did we learn? The problem with quicksort is its worst case time complexity, which is order of n square. So in worst case, we learned it is order of n square. But the better part is in case of best case and average case, it will maintain order of n log n. We also learned that in most of the cases, it is order of n log n only, and n square happens in very rare scenarios, because of which quicksort is very efficient algorithm. What about the space complexity? Space complexity, it has an average case of order of log n, but still we are considering the worst case. So let us write order of n only. So space, this is for recursion stack. So see the difference here. This is an in-place algorithm, even though it is using additional space. The reason is this additional space is not used for sorting. This additional space is used for recursion stack. So whenever you're using additional space for recursion stack, but not specifically for sorting, it won't count as out of place. It is in place algorithm, but it is using space for recursion stack, right? What about the stability? Because of the swapping you are done in between, stability is not guaranteed. So it is not a stable algorithm. Which is the next one? Next is heap sort. What about heap sort? In case of heap sort, we learned that we'll maintain a heap, which is from the given array. We'll build a heap in the array itself, and then we'll keep identifying the largest element. We'll keep moving the largest element to the right place. So this is the algorithm we used for heap sort. What about the time complexity of heap sort? We learned that you have to maintain the heap structure and do removal and heapify operations, which would mean log n for each of the n times, which is n log n. So this means heap sort will have n log n in all cases. So best case is also n log n, worst case is also n log n, and average case is also n log n. So this is with heap sort. And is heap sort taking extra space? We are building additional heap, but that is done with the array itself. We are not using any extra memory. So space complexity is constant space, no additional space used. What about the stability of the algorithm? Heap sort algorithm is not stable because you can't really guarantee the order. And is it in place? Yes, it is in place because you're not using any extra space for this. Next algorithm that we considered was counting sort. So this is where we moved on to sorting algorithms, which are non-comparison based, right? So in non-comparison based, first thing that we looked was counting sort. In case of counting sort, what did we learn? it will have different buckets for each of the bucket, in the case, in the sense, just a counter for each of the values present in the range. So counting sort not just depends on the input values, but on the range of input values that you have. According to the range, you will have one particular array element in order to keep count of all elements under that value. So depending on the range, your requirement will change. This is what we learned in counting sort. We went through the initial array, we kept track of all the counts, then we computed the cumulative array. After that, we went through the initial array in reverse order, and why exactly and all we went in deeply in the lecture. So this is how we did counting sort, and it is a non-comparison based sorting. This is important. You don't actually compare elements in between while doing counting sort. What about the time complexities? We learned that in counting sort you have to go through the array, which will take order of n. Another part is you have to go through the complete range, because your count array is based on the range, which means, let us say the range is r, whichever is larger, number of elements or the range of elements, that is what counts. So in case of counting sort, whatever be the case, you have to take order of n plus r, because range also matters, the number of elements also matters. So all the cases, best, worst, average, all are order of n plus r. What about the space complexity in case of counting sort? Space complexity, according to the range of values, you are going to have a count array. So that is the additional space used. So it will be order of r, where r is the range of values you are using. Is it stable? Yes, it is stable. And we learned in detail how stability is maintained in counting sort, right? And what about in place algorithm or not? It is not in place. Why is it not in place? Because you are using additional space for the count array. Because of that, your actual sorting process is not done inside the given input space, because of which it is not in place. The next thing is radix sort. Radix sort is what we considered. In this, what did we learn? Here, each of the number will be gone through digit by digit, and that is how we achieved sorting. So it can be number, it can be string. So either case, we'll sort it in a step by step manner by going through each of the digit or each of the letters if it is a string. So this is how we did in radix sort. And in radix sort, what did we see? We had multiple contributors. One is the number of digits in each number. If we call it as d, that is the number of digits. Then the base of the number, that also mattered, whether it is binary, whether it is decimal, whatever be the base, 2, 3, 10, whatever. And then we also have the number of elements. So these three things mattered. And what was the time complexity that we derived? We saw it is in order of d into n plus b is the order that we got. So d into n plus b, right? Number of elements and base. So one thing is, base can ideally be avoided from this, because what base will you take? Maximum you may go for hexadecimal, maybe binary, maybe decimal. Maximum is 16 hexadecimal. After that, you generally won't take, right? So we are considering, because in case you are taking some base which is larger, otherwise you can avoid the base term. Okay, order of d into n plus b. This is the worst case as well. This is the average case as well, right? So you can also write this as order of d into n if you want to avoid the term base. Otherwise, if you are counting clearly, if you are counting base as well, then it is order of d into n plus b. What about the space complexity? Space complexity, we learned, is based on the number of elements, 1, and the other part is the base, because based on the base you had to use. So order of n plus b. So again, if you want to avoid the base term, if you're not considering base term, then it will be order of n. Okay. And about radix sort, what about the stability? Yes, it is stable, because if you have two elements which are same, it will maintain the order. And is it in place? No, it is not, because you are using extra space anyway in radix sort. So the next sorting algorithm that we have, another, this is also non-comparison based, keep note of that as well. The last non-comparison based algorithm that we learned was bucket sort. In bucket sort, we learned that we were partitioning the input space into different buckets, and then we'll put elements into those buckets. We'll sort those buckets separately and then finally form a final sorted list. So in case of bucket sort, we had seen that in best case, what can happen? The best case can be that we specifically mentioned that bucket sort works better if your data is uniformly distributed. So in best case, we had seen that if it is very uniformly distributed, and let us say you have n buckets, your n buckets correspond to, you have total of n different input values. Let us say you have n buckets as well. Then each bucket will have only one element. That means sorting each bucket will take order of 1. Then you can simply combine all those, which mean it will take order of n in best case. So best case time complexity is order of n. What about the worst case time complexity? Worst case, it will be order of n square. What is important is order of average case. In average case, we learned that in bucket sort, you generally use insertion sort. The reason insertion sort is used is for smaller data sets, insertion sort is very efficient. So in a bucket, we are expecting that there will be less number of elements, because of which insertion sort will be very useful algorithm. Another one is, but the problem is when we are writing time complexity, insertion sort has a worst case of order of n square, even average case of order of n square. Because of that, when you're writing the time complexity, it won't look good. Practically, in a bucket, using insertion sort would be a very good idea. But when you are writing the time complexity, in that point, insertion sort may give you a higher time complexity. So in the bucket sort lecture, we actually derived this exact time complexity. So I'm not going through that again. It was n plus k plus, what is k? K is the number of bucket, plus n square by k in case of insertion sort. And we also said that if you want to write a better time complexity figure, then you can use merge sort. Then this n square by k term, that will come to n log n by k. That also we had seen how it came to n log n by k. So practically, insertion sort might be a better choice for bucket sort. That is why I'm keeping it here as n plus k plus n square by k. But if someone asks you what is the worst case and you want to write the best possible result, then what you can write is n plus k plus n log n by k. But there we are considering merge sort in the sorting part, right? And what about the space complexity? Space complexity, we had seen it as order of n plus k, where k is the number of buckets you have. So whether it be total number of elements, total number of buckets, whichever is larger. And what about stability? See, bucket sort is stable, but the stability is dependent on the algorithm you are using. So if you are using a stable algorithm inside, that is, if you are using insertion sort, merge sort, whatever, these are stable algorithms, then your bucket sort is also stable. Otherwise, it is not stable. Is it in place? No, it is not in place. You are having additional buckets. Then we again turn to some of the comparison based sorting algorithms. Which algorithms did we learn after this? Then after bucket sort, we learned about shell sort. And shell sort, we had seen it is a very efficient algorithm, especially it is using the natural order that is there in the data, and it is also a modified form of insertion sort. We learned about it. What is the best case time complexity? It is order of n log n. We had seen the average case is also order of n log n. And what about the worst case? In worst case, we had seen it can go to order of n square like insertion sort. So this we had detailed in specific about in shell sort lecture. So here I'm not diving into the details of it. So as of now, just remember we use the generalized form of insertion sort, and we also use the gap concept. So in shell sort, highlight was the gap concept. We learned about the gap concept, how it makes insertion sort an even better algorithm. This is the highlight part of shell sort. What about the space complexity? there is no additional space used. You are using the array that is provided. So there is order of 1, that is constant additional space. What about stability? It is not stable and it is in place. So this is it about shell sort. Why is it not stable? It is because of the gap concept, right? In gap concept, we had seen how it toys with the stability, but it improves the time complexity, and actual real time as well is improved, but it causes problem on stability of the algorithm. What about the next sorting algorithm? Next one we discussed was tree sort. In tree sort, what did we see? We formed a BST and then we tried to find the sorted order from it. And what is the best case? Best case, in if it is a balanced one, you will do it in order of n log n. And on average, you can consider a balanced tree. So you will get order of n log n. Worst case, it will be unbalanced. You will go to order of n square, right? And what about the space complexity? Formation of tree will take order of n space. So space complexity will come to order of n. The next thing is about stability. Yes, it is a stable algorithm. Is it in place? No, it is not, because you are creating additional tree. And finally, we learned about Tim sort. And Tim sort, we specifically told, is the go-to algorithm used in Python as well as Java. In Python's sorted function, Python's sort function, in Java's array.sort function. So this is a very efficient algorithm, Tim sort, especially for all the real world data sets. So we learned that for real world data sets, Tim sort is very efficient. We also learned it is a hybrid algorithm, a hybrid of merge sort and insertion sort, that too under specific conditions and certain specialities. So we detailed about that in the Tim sort lecture. What is the best case? Best thing can happen is order of n. What about the worst case? We saw that there is an order of n log n case in average and worst. So it is order of n log n in case of Tim sort, and in the worst case it will be order of n log n only. So this is it about Tim sort. What about the space complexity? Is order of n in Tim sort, and we learned about the stability and in place. So is Tim sort stable? Tim sort is stable because it is somewhat using insertion sort only, and insertion sort is a stable algorithm. And next thing is it in place or not? So is it an in place algorithm, Tim sort? Tim sort is not an in place algorithm. So this is it about Tim sort algorithm. And the last thing before we conclude with this lecture, I would like to just go through under what conditions which algorithm should you use. So in general purpose, you can generally say Tim sort is a very efficient algorithm. Specifically, it is default in Python. So it is a very efficient algorithm. Otherwise, you can generally go for merge sort. Merge sort is a quite good an algorithm to use for all the general cases. That is it about merge sort and Tim sort. Quick sort is another option which can also be used. Generally, maybe you can go for merge sort if that additional space is not an issue for you. Next thing is about speciality of insertion sort. So we learned about insertion sort. So we learned that whenever your data set is small, if you're having a smaller data set, or if it is an almost sorted data set, in both these cases, what should you use? Insertion sort is to be used in these cases. So this is the other thing that we learned from a complete set of lectures. Then whenever you have large data sets, whenever your data set is large, I didn't mean infinite data, large, let us say you have large input array or something. In such cases, we know one heap sort is effective, then a counting sort. See, with the non-comparison based algorithms, that is these three: counting sort, radix sort, and bucket sort. These three algorithms, they generally have a better time complexity compared to comparison based algorithms. So that we had learned during that time: counting sort, radix sort, and bucket sort, these three. they have better time complexities when you compare with comparison based. But the problem is the range of numbers, the base of numbers, these sort of additional constraints will come in, or maybe the number of digits. If those constraints are okay, if those are satisfied, then going for a non-comparison based algorithm will be very efficient whenever you have large data sets. So if you are okay with the additional constraints or the additional conditions that you want to know, be it with the digits, be it with the base, be it with the range of numbers, whatever, then if that is fine, you should always go for the non-comparison based algorithms. So you have counting sort, radix sort, bucket sort. So maybe you can go for counting sort or radix sort. These would be good ideas. So if this is larger data set. So this is what we learned about sorting algorithms in the last few lectures, and here we just had a overview of all those lectures. If you want a detailed analysis, please go through the respective lectures. For each of the sorting algorithm, we detailed about how it is working, what is its procedure, and so on, along with the pseudocodes, right? So this is it about the analysis of sorting algorithms.